z transform is likened to the Laplace transform. The dtft is likened to the Fourier transform. Remember those two things. So without further ado, what we're going to start with is the actual Laplace transform and work through to get the z transform. The big advantage of this is the ability to develop systems like the Laplace transform, analysis and synthesis allowed us to build filters. We could actually synthesize transfer functions. Same thing with the z. So first, start out by saying x of s is equal to the integral from 0 to infinity. This is called the unilateral Laplace transform, by the way. There is a bilateral where it starts at minus infinity. This is something in controls you'll learn more about this. But this is the common one of x of t times e to the minus st dt. That's the standard thing that we've learned before. Now I'm going to let x of t be the sample form. That one too. X of t sample be equal to x of t times this infinite series of delta functions of x, really delta here of t minus nts. All right, n is just an integer value. Ts is going to be the sampling interval. We did this exact same thing for the dtft. Y'all recall this before? So now I can also say that this x sampled of t is actually equal to the summation from n equals minus infinity to infinity of x of nts times delta of t minus nts. Now the reason I did this is the only time this function x of t is going to have a value that's meaningful is when t is equal to nts. That's when the delta function will turn on. So again, this is really just sampling this thing. This is called the comb function. It's a bed of nails. You're multiplying that times x of t, so you're getting finite. We're really getting discrete values, right? We don't have continuous values. Now, once we have this, if you think about it, just for a picture, if this is t, and x of t looks like this, then I have x of nts. What I'm doing is extracting the value at specific times here, where this would be simply ts, and this would be x s of t. Does everybody follow me on that? I'm not going to spend much time on this. It's not hard to understand. Now, when I take this and put it in here, then I end up with the integral from 0 to infinity of the summation of n equals minus infinity to infinity of x of nts times delta of t minus nts here times e to the minus st dt. I'm going to hope one of these markers is not there. Maybe.
Forget about it.
That one's better. All right. Now, at this point, the only thing I did is stick in the sampled signal where the actual continuous time signal was. This is still a legitimate Laplace transform. Now the idea is this. Because this is nts, follow me, the argument is nts. Here, the t is there. That's the only thing that's a function of time. It's with the delta function. So when we have a delta function multiplying anything inside a kernel of integration, we integrate, we extract the value of that other function at the time the delta function turns on. Does everybody recall this class? This is important. So now I can say that this, actually, x of s, here is equal to the summation of x of nts here times e to the minus s times nts, where n goes from 0 to infinity, or minus infinity to infinity. I have a comment here. Now you'll notice when I did the sampled signal, I started it at minus infinity. You follow me on this? Actually, what we're going to do is use just the unilateral z transform. That assumes that the value of x of n, or x of t, is 0 for all negative values. Pretty much always. There's a couple of exceptions. So, go ahead.
Oh, how were you able to replace the t on e to nts?
When does this delta function turn on?
At t equals nts?
Right, and what does that do? Extract the value of e to the minus st at nts, doesn't it?
Well, I just thought it was. I guess it's part of the summation too.
What if? Well, remember, I'm going to take this integration inside, right? So now when I do that integration, right, it's still from where? 0 to infinity, correct?
Mm-hmm.
The only thing I have to do is look at what happens when this delta function turns on, right? Turns on at NTS, so I replace T by NTS, correct?
Okay. Okay.
That's it. And we've done this the same exact thing for the DTFT. If you look back and think, y'all remember this class? It's important you see what I'm doing here. Now, at this point, what we do is clean it up a little. We suppress TS. Technically, we use square brackets here, and then we do something else. I'm going to say now S of S is actually going to turn into something called X of Z. And here, I'll show you how. Here I'm going to have this summation, and now we'll just start at 0 to infinity because I'm going to assume X of T is equal to 0 for T less than or equal to 0 for the sampled signal, as well as continuous time. Understand, class? The values for T less than 0 are assumed 0, or they're not of interest. There's one exception. But for now, you with me on this, class? So it starts at 0, and now I'm going to say this becomes X, and they use a square bracket here to indicate that now these are integer values, but there is some TS that's not stated. We don't know what it is. Just like when you did your circuits problems, they didn't state omega all the time in everything. They would have 10 at an angle of 30 degrees, then they'd like have J 30 ohms and 10 and minus J5. Do y'all remember that? The omega was suppressed. Go ahead.
So since it's T at NTS, does that make T a complex value?
Now, just follow me on this. T is real, all right? But S is complex. S has sigma plus J omega. Remember that?
Yeah, I guess my real question is like, why is it N times TS? Would it not just be NT?
N is an integer. TS is a sampling interval. If it's N equals 1, it's the first sampling interval. If N equal 2, it'd be the second. Sigma, the S is where the complex value comes in. S is sigma plus J omega, right?
It is.
All right, just watch me. You'll see this. So now this is E to the minus S, right, times TS to the nth power. Do you agree with that? With me? Now I'm going to do one other thing. I'm going to say this is really equal to, I can put N in here. But what I want to do is match the standard form of the Z transform, which is N equals 0 to infinity, X of N times Z to the minus N. That's the standard form. Are you with me? That's the standard form. Which means what? It means that here I have E to the minus STS, right, times N is equal to Z to the minus N. Does everybody follow me on this one? I'm equating the Z to the minus N to E to the minus STS times N. Yeah.
I'm sorry, but is the S a subscript of the T?
No, I mean, TS, here, I'm sorry. What I should do is this. Let me just say it's E to the minus ST times N. TS sampling is this. It meant sampling.
That's what was throwing me off.
T, I'm trying not to say it's the period. It's the sampling interval. Follow me on this, guys? That's all the capital T indicates. It's the interval in time between the sampled points. Now, if this is the case, I'll just leave it as T since you, actually that's a good point. This is minus N. Now, look right there. What does that make Z?
E to the negative ST?
Plus ST, right? The minus 10 cancels. Do you all agree with me, class? How many see this right here? Now listen to me carefully. S is a complex number. That means it is real and imaginary, which means one thing. Z itself, and just write this down, and I'll spend a lot of time on this. Z itself now has some magnitude rho. Rho is just the radial distance. I choose rho because you've had polar coordinates. Usually the magnitude or the length of the line is indicated by a rho, isn't it? And it's going to be at some angle, E to the J omega. So if you think about this in a complex plane, and this is the Z plane. All right, this would be the real axis, and this would be the imaginary. And now we have Z is going to be some length from here to here that has a value of rho. That's some angle E to the J omega. Everybody got that? That's all it is. Remember before when we had the S domain, what did you have? You had sigma was the real part, and the imaginary part was j omega, right, for us? Here it's different. And the reason is because this is to an exponential power. If you think about this just for a second, if I put this is really e to the sigma times e to the j omega times e to the t, right? What do you think about it? You agree with that, class? Now this right here is a magnitude. And this is an angle. And that's really what the Z transform is. A lot of this will become clear in time. You're going to have to just go with me now. So just think about what Z means. Magnitude and angle. Right now, there are so many questions and uncertainties in your mind about why we're doing it. But you'll see, just like you did with Laplace. Laplace transform and with Fourier transforms going into the DTFT and finally the DFT. All right, now that's the definition of the Z transform. This is it, but let me just put it explicitly up and go get rid of some of this stuff so I can do a few of them. This will make sense to you in time. Big thing about a Z transform that bothers people more so than anything is because you're used to integrations, but sums are not something that at least I was real familiar with what happens, the forms that they take in the convergence. And you got to understand with real-time processing, everything is done with discrete values that are actually quantized into digital information. So what we're doing is we're working towards the actual real digital signal processing that goes on day to day and everything we do. Now, this is the formal definition of x of z. It's equal to the summation of x of n, and normally these are square brackets, but mine aren't, where n starts at 0 and goes to infinity. This is the unilateral Z transform. It's the definition that we're going to use. You'll see when you get into digital signal processing, some of you will, they actually started at minus infinity a lot of times. It gives you more, an ability to realize more systems, but I can't go there now. Just understand, you will see where this starts at minus infinity, all right, in time, if you take digital signal processing, times z to the minus n. Now that's the Z transform, that argument Z. Let me liken this to the DTFT. So this is the Z transform. Right? Now when we looked at the DTFT, it was equal to what? X of omega was equal to the summation n equals minus infinity to infinity of x of n times e to the minus j and omega, right? That's the DTFT that we developed. Now let's take a look at this. If we look at these two and we allow one, remember what z is. Z is equal to some magnitude rho times e to the j omega, right? Now, if, and only if x of n is 0 for n less than 0, if that's the case, then you can say that x of omega is equal to x of z, with z being equal to j omega. Now just take a look at that. If z is equal to j, if z is equal to j omega, I mean z is equal to e to the j omega, rho is 1, is it not, class?
Yes.
Please take a look at this. So in that case, the Z transform is the DTFT. And it's just like with the Laplace transform. Do you remember with the Laplace transform? If you let S be equal to j omega only, and x of t was 0 for t less than 0, the two became the same. Do you understand that, class? It's the same thing here. Please realize this. So that means if that's the case, DTFT and Z are the same. If all the values for n less than 0 are 0, you can get the DTFT from the Z transform. In other words, understand, class? A couple things about the Z transform. There's something that's real important. Well, I got this in my notes. Let me develop this. There's a thing called region of convergence. Do you all remember with stability with Laplace transforms? What was the singular thing about stability that you got? Anybody? This is important. How many know this without saying it? I'm not going to call it. Laplace transform. There's one thing that's so critical for stability. It has to do with the complex plane. Go ahead.
Does it have to be in the...
All the poles have to be in the left half plane. How many remember that? All right, with Laplace transform, stability means all the poles in the left half plane. For Z transform to actually work, and by the way, what did that actually mean? It meant the integral of the x of t e to the minus st dt was finite, right? Do you all remember that? That's what those poles in the left hand plane mean. Now, with the Z transform, we have something like that. So if we have x of z here equal to the summation from n equals 0 to infinity of x of n times z to the minus n, there's values of z that will allow that. This has to be less than infinity. It has to be finite. And the values that will allow that to occur are the z values that determine what's called the region of convergence. So for this to take place, we have something called a region of convergence. And it's called ROC. Let me give you an example of some of these. Here's what I want to do. Go work through some Z transforms. You know how before what I always did is I get you a set of basis functions you had to know the transform pairs of, right? Usually 4 to 6 of them. And after that, use properties to get everything else. Do y'all remember that class? Now a lot of times you remember the more complex ones because you see them so often. But we use properties to get the other ones. So first, let me do a few of these and explain the region of convergence. And it's just like the region of stability for Laplace. So for here, I'll start with delta of n. If I have delta of n, put it in there, what do you get as the transform of that? Just look at it.
1 over c.
If you put delta of n in here, delta of n turns on at n equals 0, right? All right, what's the value of delta of n at n equals 0? 1, not infinity, 1, right? This is a discrete, right, folks? So at n equals 0, what's z to the 0? 1. In other words, this is 1. No surprise there. All right? The transform of a delta function almost always is 1. Matter of fact, I can't think of the case it's not. If it's not, then there's something going on that I don't know. If you have delta n minus n naught, what does that transform? By looking at the definition. Do it in your head. Where does the delta function turn on at? N equals n naught, right? All right, what do you evaluate? Z to the minus n naught. Right? This is not hard to do. Do you agree with me? Keep going on this. Next one I'm going to do. Let's do this one. Let's do a to the n u of n. Now this one I can talk about the region of convergence. So if I do that, I'm going to do it using this functional form. Let me do it over here. By the way, I walked in and somebody told me that we're supposed to get hail tonight. Is that right? What? Is that right or not? Just rain? Well, that's this disinformation. When's it supposed to hit? Anyone?
Right now, like 4.
4 o'clock? Last thing I need is hail. I can handle a lot of stuff but not right now. All right, let's do this one. Yeah, go check weather.com or wherever you go. Give me an update. Let's go over here and do this. X of z now, right? Here z is going to be, or x of n is a to the nu of n. It's going to be equal to, work with me, and most of you know this by the way, 0 to infinity of what? A to the n times u of n, which starts at 0, right? So it takes care of that, times z to the minus n, right? Well, how do I do that series? This is a typical question people ask when you're being interviewed. What's that series going to go to? Well, how about I do it this way? I'll take the sum, n equals 0 to infinity of the, how about we call it a over z to the n? Do you agree with that? Z to the minus n is really what? 1 over z to the n, isn't it, class? What does that series converge to? Now, this is one you have to know. That's going to go to what? 1 minus something that'll go to 0, right? Over 1 minus a over z. Do y'all remember how to get that? I mean, how many remember the geometric series? If you don't remember it exactly, you've surely seen it several times in this class, and you'll need to know that for the final exam. You have to know the geometric series. If you don't, I'll put it up here one last time. The summation from n equals q1 to q2 of any a to the n. Now, a can be anything. It can be real and complex. N is an integer. This is going to be equal to a to the q, or really a to the q1 minus a to the q2 plus 1 over 1 minus a. Now, I've proved that. I'm not going to bother right now, but you've seen it several times, at least 3 or 4 times, just doing the basic proofs for DTFTs. I remember that. And plus convolution. We did use the discrete time convolution. Now, for this one here, what I'm going to do is multiply top and bottom by z. This is the common way it's done. And you get that. Now remember, z has a magnitude, and it's at an angle, so it's a complex number. When I look at this, I'm going to ask you one and only one question. If you looked at this sum, what values of a and z would make, or what values of the ratio of a to z make that finite? Magnitude of a over z
Less than 1.
less than 1, right? Or a magnitude greater than magnitude of z, or really z greater than a. Follow me? That way it will converge, definitely converge. Do y'all agree with that? Now just think of the opposite. If the ratio of a to z, magnitude of that was greater than 1, say 2. Well, if you had 2 to the n, what happens as you get higher and higher values of n? It's going up, 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 and the summation is going to infinity fast. Do you agree, class? So this tells me the region of convergence right here. Magnitude of a, magnitude of z greater than magnitude of a, and that's region of convergence. Let me show you what that looks like. So you get you're starting to get a peek of what we're doing now. When we look in the z plane, now it looks like this. We're going to have something that's now a radial distance of a, magnitude of a. We're going to draw a circle, and everything outside that circle, where z greater than a, this is the real axis here, and this is the imaginary axis here. All values of z greater than a magnitude of a will allow that series to converge. That's called a region of convergence. Now, it means it's stable. I can't go there now, but later hopefully you will see how this allows us to build stable systems. Remember with h of s, the one thing you wanted to make sure is the poles were all in the left-hand plane. Any of the right-hand plane means if you had an impulse or almost any input signal, it would cause the output to eventually go to infinity. It would be unstable, right? Same deal here with the z. When we're going to be synthesizing stuff with z transforms and stuff, really using z transform properties and things like that, you're going to see this region of convergence will be important. Understand, class? And I don't want to spend a lot of time on it right now until I get through the z transform stuff. So this is a z transform for a typical a to the n unit, right? What do you think the transform is? Just look at this now. I'm going to raise this. What do you, oh no, I'll put it here. This is what? It's z over z minus a, or it's equal to just 1 over 1 minus a, z minus 1. Either one's the same thing. What happens to just u of n, class? This one you got, right? For u of n, what is it? Just look at the one above it. What would you make a to have u of n? 1. 1 to the 0 to the n is still 0. You're thinking about, what you want to do is make a 1, don't you? Yeah. If a is 1, then you have that. So this is going to be z over z minus 1. Got me on this? Now, you take a look. I've actually used a property to get this one without telling you, but we actually evaluate the function. Here's 4 functions, right? Right off the bat. Now I'm going to show you a couple of properties. You can almost tell where I'm going to go. Because you know almost invariably, you're going to see a cosine multiplier and a sine multiplier, right, class? Almost invariably. And we've already, well, we're going to go ahead and do it with the sine and cosine because we've got this one. right here. So let me do it. I'll leave that there. All right, now I'll prove one of these two. I'm not proving both, but I'm going to prove one of the two of them. Suppose I say I want the transform of x of n times sine of omega naught n. I want that one. The way you get these, and the way you get cosine too, is by taking the sine and turning it into the exponential arguments using Euler's. Are you with me, class? So if you do that with exponential arguments, what do you get? You have x of n, right, times e to the j, go ahead, omega naught n minus e to the minus j omega naught n, right, over 2j, right? Do you all agree with me, class? All right, now I'll come down here and I'm going to say that's x of n, right, e to the j omega naught n over 2, and I'll put I'll leave the j here, minus x of n times e to the minus j omega naught n over 2j. Now, follow me on this one. There's nothing tricky here. I just went ahead and multiplied. Now when I want this one, just follow me. And this is something I'm going to do a property on right here.
Was there supposed to be a negative in front of that j on the first one? Oh yeah, that should be a plus.
Pardon me?
The first fraction you got there?
Plus. My bad. Should be a plus then. Whoever said it's right. Next thing I'm going to do is right here is a property. If I have x of n times e to the an, and I want to know the transform, assuming I know x of n goes to x of z. All right? I know that top property. Are you with me? I'm going to get this property next. This is a simple property. So to do it, I take the summation, and I use the definition of the z transform. I put in x of n times this, e to the an times z to the minus n. N goes from 0 to infinity. This would be the z transform of this. Do you agree with me, everyone? Let me stop and make sure you see it. If I put this as my argument for the z transform, not just x of n, but x of n, e to the an. Follow me, everyone? Now what happens? Well, this is the same thing as what? The summation here, n equals 0 to infinity, right? And now I can say x of n times z over e, right, to the minus a to the nth power. I can do it this way. Yeah, e to the a to the nth power. Take a look at that. Do you agree with me, everyone, class? What I need to do is what? I need z to the minus n there, right? If I take 1 over that, that's e, this right here, e to the an is equal to, really what? It's 1 over e to the a to the minus n, is it not? Just take a look. Do you all agree with that?
Yeah.
E to the an, well, it's 1 over a, e to the minus n, right? Now, the reason I wanted that is I want this. Now I take this times that, and I get this, right?
So it should be negative in front of the n.
Pardon me?
Yeah,
you're right. Thank you. That's right. Do you agree, class? Now, what is that? Well, isn't that really the z transform of this? Excuse me, this is x of n. I got x of z there. This is x of n, pardon. That's x of n. Isn't this really, this right here is what? X of not z, but z over e to the a. Do y'all see that? Because What was to the minus nth power is what is that transform's argument. Before it was just z. Now I divided z by e to the a, and since I know this is the definition of the z transform, whatever that z is, and remember z represents a dummy variable. Instead of z, if I put k over w, if I have k over w to the minus n, it means that z is now becoming k over w. Do you follow me on this, class? Here, I wanted to make sure the argument was z, I wanted to get everything over here, so it's x of n times something to the minus n power. And then the transform of that is the z transform with z replaced by z over e to the a. Follow me? Or you can say it's equal to x of e to the minus a times z. Now I wanted to do that to make sure you see this. This is a property. It's multiplied by an exponential, e to the an. Can everybody see this right here? How many see this? Can you all see it and understand this? Why did I do that? Because now look over here. Look at the first one. What do I really have? I have x of n, right? And my exponential right here that I'm multiplying it by is what? I have e to the j omega naught n, right? And I'm equating that to x of n times e to the a n. Correct, class? Can everybody see that? How many did right? What's the reason I did that? So you see that a is equal to what? J omega naught. That's it. Do you all see that? Everybody? Okay. Now, if you see that, then what happens here? When we do this transform right here, what do we get? I'll leave the 1 over 2j out in front. I have 1 over 2j. Now, the transform of this is going to be what? Just x of, go ahead. Or times e to the minus j omega naught. Correct, class? Minus x of z, go ahead, e to the plus j omega naught. Do you all agree with me? The z transform now, if you have x of n goes to x of z, you take that z transform and you replace the argument z with this. Right? And to be frank about it, now if I take the j and take 1 over, what is 1 over j? Minus j. If I do that, here's what happens. I can say now I get j over 2 times x of, and then it's z e to the j omega naught minus x of z to the e to the minus j omega naught. And that's the sign. That is the transform of x of n, right, times the sine of omega naught n. I'll get to some specific examples. Now this looks very similar to the DTFT and to a lot of other transforms where we had a sinusoidal multiplier, or just think of continuous time. Remember, if you had what? X of t times sine omega naught t, and you got the Fourier transform of it, what was it? It was j over 2 in the front, right? And then you took x of omega plus omega naught minus x of omega minus omega naught. Do y'all remember that? It was a difference in frequencies. Now, you don't take the difference, you do the multiply by the actual frequency, e to the j omega naught times z. Understand, class? And this is what happens if you have a sine multiplier. Please write this one down. You need to know that. The book does not make this explicit, so you need to write this down. Write that one down. I'll give you the next one too. That's the sine multiplier. For cosine, I don't think they do. If you look at the z transform tables, I don't believe they have this. I'm going to go ahead and show you the cosine one and then do something. I want to do a couple of these that I think are really important to see. So the next one I do is this one. I'll leave that up there. Next one I do is this. Suppose I have x of n times cosine of omega naught n. I use the omega naught there for a reason. The book just calls it omega. Because anytime you get a sub-zero, it means it's a singular value in my book. When you did DTFT, if you just had omega, that could go from minus pi to pi, right? It really had a continuous possible number of values. I just do this to distinguish it. Now for this one, you all see how that cosine would become what? E to the j omega naught right? Over 2 plus e to the minus j omega naught n over 2. Correct, class? With that one, you're going to get a same basic thing, only it'll look like this. I'm not going to do this one for the sake of time. You're going to get 1/2 here, not the j over 2, and then you're going to get simply x of z times e to the j omega naught plus x of z times e to the minus j omega naught. Does anybody have your book here? Can you look and see if he has these in the z transform properties?
He does not.
Huh?
He does not.
Please write these down. They're extremely valuable. And you'll need to know them. They make things a lot easier, knowing this property. Now, remember, once you have x of z for this, you simply get this by just taking that transform and multiplying, wherever is the z, you multiply it by e to the j omega naught. Let me show you an example of this in action. And he does have what I'm about to show you. Because this, we'll get to some more properties in a second. But the properties are about the same as the DTFT. And really, almost all these properties you'll see. So let's do this one, and work with me on this one. This is typical. Suppose I gave you this for a quiz. I give you a to the n times cosine of omega naught n times u of n. All right? And I want the transform of that. I know you just were introduced to z transforms today, so you're a little rusty as far as some of the stuff goes. In other words, you're completely unfamiliar with it. But you realize that this, a to the n u of n, I gave you is this. Correct, class?
Yeah.
So we check that box. And I also gave you modulation just above it, if it's multiplied by cosine, right? So now we go ahead and apply the theory. So I say the cosine multiplier is going to do one thing. First, it puts the 1/2, right? Got me on this? Just put 1/2 out in front. And then I take my z transform that I know, right here, and wherever I see a z, I put z times e to the j omega naught. Right? So now I put z e to the j omega naught here over z e to the j omega naught minus a, right? And I have plus z times e to the minus j omega naught over z e to the minus j omega naught minus a. I'm going to block it. Put a couple of lines here. Y'all see what I'm doing. I replace z by z times e to the j omega naught. Can everybody see this, class? Far back, far back. Now I want to simplify. Remember, that's good, that's correct, but you try to condense these things into forms that make a little more sense visually. And this is what you should have in the book. If you take a look at this, right, I'm going to leave the 1/2 alone for now. Now, look, y'all realize I can get a common denominator. If I multiply this times this, I get a common denominator. Do you give me that, class? So if I multiply this by this, I have z to the j omega naught times z e to the minus j omega naught. Isn't that z squared, class? This times this just gives me z squared, right? The angular portions cancel. How many see this? The last two terms, minus a times minus a is a squared, right? So I know I'm going to have a plus a squared somewhere out here. Now what about the middle terms, the cross terms? I have minus az e to the minus j omega naught, and I have minus az e to the plus j omega naught. Does everybody see that? So I have z and a and a minus sign common. Z, A, and a minus sign. Now what is e to the j omega naught plus e to the minus j omega naught? Class? 2 times cosine of omega naught. How many know that? All right, Euler's is critical, you know. You have to know Euler's like the back of your head, or you really aren't going to survive very well in engineering. So Euler says if cosine of omega naught is equal to e to the j omega naught plus e to the minus j omega naught over 2, right? Therefore, if I have just these, I multiply by 2, and I get that. Understand, everyone? Are you with me? So now I can say that this times this, and this times this brings out a minus AZ times really 2, and then it's going to be times cosine of omega naught. Now that's on the bottom. What's on the top? Make that what it was. Make that squared. Take a look on the top. Well, I have this times this, correct? You agree with me? What do you get? I have z e to the minus j omega naught times e to the plus j omega naught, or z squared, right? Then I have minus a z e to the j omega naught, right? So I have minus a z e to the j omega naught. What about this times this? What do I get? Well, z to the j omega naught times z to the minus j omega naught is z squared, right? So that gives me a 2z squared, doesn't it? And what about the next part? Minus a z e to the minus j omega naught, right? So I have minus a z e to the minus j omega naught. How many see what's up now? Look at these two. Isn't that really what? Can I figure out? I can factor out a minus az, and I'm left with e to the j omega naught plus e to the minus j omega naught, right? What is that? Say it. Cosine, right? 2 cosine, actually. So this top part right here becomes 2az cosine of omega naught, right there. And in fact, this is what he should have, well, he get rid of that 1/2 and that 2. But this should be the transform he has for this, for a to the n, when I have a to the n cosine of omega naught n u of n, right here, this is what the transform is. Take a look in your book, if anybody has one. Is that what he has there?
Yes, sir.
Now, I'm going to say this right here. I condensed it, right? Again, a Z transform using the modulation theory I gave you. You'll have to know this very well. I can tell you that right now. Next one I'm going to do is the sign. You can almost tell that this will become rather, I mean, it's the similarities are so over the top because they're exactly what we've been doing the whole time. The modulation theory, when you have a sine, you have a j over 2. A cosine, you just have 1/2 in front. And for a sine, you subtract 2 things, right, with the shift property at work, and when they're actually the cosine, you add the actual transforms after their shift. Correct, class? So here we're going to go ahead and do the sine. Suppose I have a to the n times the sine of omega naught n times u of n. All right, people, let's go. What do we do first? Anyone? What's that? Well, I think you're ahead of me. How about we first identify this is the actual x of z we want? Y'all agree with that? Follow me on that? That's a given. We're assuming we know that. After that, now we go ahead with what he said and get the j over 2 business. Let me actually make that arrow a little shorter. And now I'm going to put j over 2. Now I take this, but instead of z, I put z e to the j omega naught, right? Over z e to the j omega naught minus a minus z e to the minus j omega naught over z e to the minus j omega naught minus a. Do y'all agree with me here? Again, I've just done the property. I used modulation with a sine, and I knew the x and z, and I just modified. Now, we can continue down the line here. But you all see what I'm going to do is get a common denominator. I'm going to multiply this times this, and I'm going to get the same common denominator as right there. That's the guaranteed. So now I know what I'm going to have is this. I'm going to have z squared, right, minus 2az cosine of omega naught plus a squared. That I know I'm going to have, and you can prove that. But on top, what's the difference? That minus sign causes something to happen. Follow me. I have z to the j omega naught times z to the minus j omega naught, right? That's z squared. Do you agree with me? I have a z squared. Then I have minus a times that, so it's minus az times e to the j omega naught. Now I have minus this times this, or minus the quantity z squared right here. This times this will give me z squared. And then I have minus right there, and it's going to be az e to the minus j omega naught. I'm going to get out of your way so you can see this. Please make sure you see what I've done here. I've got a common denominator, and now I adjust the top portion, or the numerator, to account for that. Now, what do you see happening here, just by inspection? I'm going to take, I'll leave the z squared minus 2az. You're right about that. Denominator is fine. Y'all see z squared minus z squared is gone. Yes, sir?
You still need the j over 2.
Yeah, you do. You do. Thank you. I'm looking at time here, and I'm getting a little light on time. Do you agree with that? Thank you. All right, what else happens here? The z squareds go, correct, class? Next thing, I have minus az e to the j omega naught, but it's minus a minus or plus az e to the minus j omega naught, right? You'll see there's a difference. Let me just cut to the chase. That's going to be 2az sine of omega naught over j, all right? Are you? If you look at this and this, what you actually get is minus, let me put the 1/2 here, or j over 2 here, out front. And then you can see this. This is going to be minus az, and then we're going to have e to the j omega naught minus e to the minus j omega naught here. Take a look at that. I just factored out the e to the, or the minus az, correct? Please take one look at this. Let me finish this thought. What's this right here?
2j.
Isn't that 2j sine of that argument, class?
Yeah.
All right, now notice what happens. When you get j times j, it is minus 1, right? With a minus is plus. Therefore, this transform actually is this. It becomes, and in your book it should have a az times sine of omega naught here over z squared minus 2az cosine of omega naught plus a squared. If you have a book, can you see if that transforms the form they have it?
It was there.
All right, that shows you now I've got transform, I've used modulation, both sine and cosine modulation on a damped exponential, right? And I got it. Now this is something that crops up all the time, this stuff. I want to tell you one other thing too. Many, many times, this argument, cosine of omega naught will be 0. For instance, if omega naught is pi over 2, the cosine of pi over 2 is 0. Follow me? So that can happen very easily. Another thing over here, if the cosine 0, I have z squared over z squared plus a squared. On this one, if the cosine 0, then I have az because the sine of pi over 2 is 1. Az over z squared plus a squared. Just remember that. I'm out of time. I'm going to give you some things to do with z transforms. We'll go through the properties in detail next time. I didn't want to just do overheads on this. When profs do overheads and they don't apply to things, it absolutely just goes right over your head. I'm trying to make this thing I'm trying to apply everything I show you to something. And next time we'll do a lot more. Now this z transform stuff, stay up with it, all right? Because all this stuff gets linked together. It's very important. All right.
It's not world travel.